2.4, which is piecewise functions. They're peaceful functions. No, not that kind of piece. They're in pieces. We'll talk about it. So, piecewise functions. So first off, let's just start with basic 6 functions. They're on the sideboard. I'll write them up here as well. These are the basic 6 that we're going to spend a lot of time with today and Thursday. So first off, y equals x squared. You probably know half these or more. What does y equals x squared look like? It's the U-shaped parabola going up, right? And then when you take that 2 and you move it around to the root,
like half, probably.
That's like that. I always call it the firework. Looks like you set it down in the ground and it shot off to the right there. So that's the only one that just goes one way. All the rest of them go left and right. So like that. And then we come up here and we'll go, okay, now what about third power? What does third power look like? Yeah, that's the snake.
We didn't have any specific name for that.
And then now I want to take that 3 and put it in the hook. See, I keep doing a 2 power 2 root, 3 power 3 root.
V-shape?
What does that look? Yeah, what does a 3 root cube root look like?
V-shape? Y-shape? V-shape? V?
Maybe we're. I don't know it by that name.
It's a sideways snake.
I always think of it as a sideways snake. But as long as you're thinking of that, it's all good. So it's the same thing. It just goes sideways. See how the root graphs go more sideways and the power graphs go more up and down? You know what I mean? Like x squared and x cubed, they go up and down real fast, don't they? Mm-hmm. Whereas the root graphs are more sideways than they are up and down because they're slow growth functions. Because roots don't get big very fast. Root of 100 is only 10. But if you take 100 and square it, it's 10,000. Right? So power functions get big real fast. Root functions don't. All right? Now, 2 more. Absolute value of x. You know what that one looks like?
V.
Yeah, it's a V. Goes right up. Starts at the origin. Notice how all these are centered at the origin, aren't they? We're going to move them around and flip them and stuff in about an hour. But for now, they're all at the origin. Last one is kind of the trickiest. It's y equals 1 over x. That one has asymptote lines at the axes and diagonal branches. So again, they're on the sideboard. Those are the basic 6. So we're going to take those basic 6. We're not going to do much with them in this section, but then in 2.5, in about an hour, we're going to do all kinds. We're going to flip them, rotate them, stretch them, compress them, move them, do all kinds of things. We're not going to rotate them. That's not true. But all the rest. Do all the rest. Okay, so those are the basic 6. You probably already know a lot of them. So now they're going to ask us some questions about those really easy stuff, just naming stuff. So they're going to give you one like this, like question number 1 is something like this. They're going to go, okay, what's the name of that one? And it's the square function. So I'm going to skip all those. Those would be super easy for you here. So f of x equals 2x, and it wants me to graph it. Okay, so how do we graph f of x equals 2x?
Well, you would look at...
Well, it's not really one of those 6. It's too simple, actually, for those. F of x is really y, isn't it? Remember, function values are y values.
Oh.
F, G, H. So it's just y equals 2x. So what is it?
Y-intercept is 0.
Yeah, it's just a line, isn't it? It's just a straight line. You can do the mx plus b thing with the y-intercept and the slope, or you could make a little table if you want. Whatever. I'm going to do a little table, whichever way you prefer. Plug in 0 for x. What does y equal? 2 times 0, that's 0. Plug in 1. Y is 2 times 1, 2. Graph it over 0, 0, over 1, up 2. There it is, done. Easy, right? I'm going quick, I know, but there's hard stuff. I'll slow down when we get to the hard stuff. Good to there. So just graph a line, make a table like you already know how to do. Good. You could plug in more points. You could do the slope. You know, you could do the slope method. But I could have said, look, 0. There's like a 0 out there. That's where you start. Right. That's the other method of graphing, which is totally fine as well, whichever you prefer. That would start here at 0. That means that's the y-intercept, huh? That's where the graph hits the y-axis at a height of 0, and the slope is 2 over 1. Remember, that's rise over run means go up to over 1. Sure enough, that's the next dot. Same thing. Make a table, do the mx plus b, whichever you prefer. There's the line. Let's move on. Okay, so number 9 is a piecewise function. So here we are. This is a function in pieces. It's like Frankenstein. I just thought of it. I like my analogy. Remember Frankenstein?
Scary monster.
Well,
He was misunderstood.
well, I wasn't going to get all into the psyche or his moral or emotional life. I was just going to say he's in pieces, right?
No.
They put different pieces together, right? Am I remembering that right? Yeah, somebody else's brain, somebody else's body, right? Frankenstein. So that's what a piecewise function is like. They're piecing together different graphs into one new thing. That's what the rest of this section is all about. Piecewise functions. So here's our first one. So basically it's a function in pieces. So they're saying, now how do you know, well, which piece exists where? If x is less than 0, and this is y out here, as remember, f of x, function values are y values. If x is less than 0, you use y equals x squared. If x equals 0, you just do negative 2. If x is greater than 0, you use that one. So you use different functions for different x values.
Write a drum program.
Does that make sense? Let's get into the particulars now. So the first thing, the answer is already there for you. They're saying, all right, what is f of negative 3? You can see the answer is 9. How'd they get that? What did they do? So the x value, this, remember, it's always x that you plug in the parentheses. Right? So x is negative 3. So am I going to plug into the top one, the middle one, or the bottom one? For x negative 3. It says x values less than 0. Less than 0 means negative, huh?
Yeah.
For negative x values, plug into that, please. So we plug negative 3 squared. That's how they got 9. Does that make sense? They plugged into x squared. So you're always looking and saying, which one do I plug into? Rebecca.
So those are the equations that we choose from.
Yeah, right. Right. It's those. It's going to be one of those three, the top, middle, or bottom, always, depending on your x value. Exactly. All right, let's do part B. My x value is 0.
F of 0.
So which one am I going to...
Negative 2.
The negative 2. And notice there's not, because that's if x is 0. Negative 2, 0. There's not even an x. It's just negative 2.
Right.
You don't actually just throw away the x. There's nowhere to do anything with the x. You just say negative 2. Good?
So it's not going to be negative 2 times 0 because there's no x.
Right, because if it was negative 2x,
Right.
then I would plug in that x as 0, but it's just negative 2. No x at all. And then the bottom one, if x is greater than 0.
3x plus 3.
What's greater than 0?
15.
Positive. So in this x value on part C, the x value is 4. Positive 4. That's greater than 0. So I'm going to plug into the bottom one. I'm going to plug into 3x plus 3. I'm going to plug in the 4 there.
48.
12 plus 3, 15. That's how they got that.
Oh, it's a 4 up there.
And there we go. Is that making sense? So you plug into different functions for different x values. They're different functions pieced together. Like Frankenstein. It's in pieces.
They're always going to give us the conditions we need.
They'll always give you those conditions. That way you know which one to use when. Exactly. Exactly. Good, Douglas. Yeah. All right. Okay. There we go. There's a function. Oh, what are they? Okay, and the questions, part A. 0, part B, 1, C, 5, part D, 6. Okay. So there's our questions. Can you do that one? Try that one. A, B, C, and D. Using that piecewise function, that function in pieces.
Is that 0 or 1? Can
What's that?
the first one?
F of 0?
0.
Yeah, F of 0. How are we doing? So decide whether to plug into the top function for each of those 0, 1, 5, and 6. For each of those plugged in, you're either going to need to plug into the top function, 2x minus 1, or the bottom function, x cubed minus 3. depending on the x value. So if the x value is between -2 and 5, you plug into the top function, huh? If the x value is between 5 and 6, you plug into the bottom function. So let's try part A. F of 0. So the x is always what's in the parentheses, huh? So if x is 0, which function am I plugging into, the top one or the bottom one?
The top one.
The top one, because 0 is a number between -2 and 5. 0 is not a number between 5 and 6. So I'm not using the bottom one, I'm using the top one. So plug into 2x minus 1, plug in your 0, was that -1?
Yeah.
Good so far? We'll try part B.
One.
So part B, we're plugging in x is 1. Which function are we plugging into? The top one or the bottom one?
Top one.
Top one, because again, 1 is a number between -2 and 5. 2 times 1 minus 1, 1. Now try part C. Decide if you should plug into the top one or the bottom. Be careful, this part C is a little closer, huh? Closer call there. So x is 5. So which one should I plug into, top or bottom for 5? The top one because it's equal to 5. The bottom is only between 5 and 6, not equal to 5, huh? So top one, again, 2x minus 1. Plug in the 5 right there. 10 minus 1, 9. Everybody see why that was the top one? Because equal to 5 for the top one. Finally, the bottom one, x is 6. That's going to be the bottom equation. X cubed minus 3. Plug in the 6. 6 cubed minus 3. What is that? 216 minus, use your calculator. 213. And there we go. We all good? Because we're going to go to graphing them now. If you've got that. This is kind of the warm-up. They're just getting your feet wet with the main idea of plugging into different functions in different zones. Now we're going to graph them. If you're good with that, no questions? Here it is. They're going to ask me a million questions. They're going to ask me for the intercepts, the domain, the range, and then finally the graph. But really, we should start with the graph. Because once we have the picture, all the rest of the questions will be easily answered. So it's kind of weird the way they do the homework. They have the graph come last. But really, you should do the graph first. Because, you know, like the old saying, picture worth 1,000 words. The graph will be worth 1,000 questions. Once we have the graph, all the questions will be easy. So let's get the graph. Let's graph that function. What it's going to be is two functions pieced together. Again, like Frankenstein. So it's up to us to figure out which ones go where. So it's all about these conditions over here, huh? See what it says over there? You're using the top one for x values less than 1, and you're using the bottom equation function for x values greater than or equal to 1, right of 1. So it looks like the dividing line is at 1, isn't it? Now I like to go over to 1 and put a dotted line. Not required, you don't have to, but I've noticed it helps students since I started doing it. So I'm going to put it in, because that's the separate, that's like the stitching on Frankenstein, where one piece connects to the other piece. That's what's going on with the graph. We're stitching together two graphs right at that barrier, right at x equals 1, because that's the barrier they have in the conditional statements. the if x is less than 1 and if x is greater than or equal to 1. Okay, so let me put the different functions in the different zones in which they belong. So for x values less than 1, that's on the left side of 1, huh? You're supposed to have this one. So I'm going to go y equals minus 3x plus 4 left of 1. And over on the right of 1, greater than or equal to 1, you're supposed to have y equals 3x minus 2. So I just go ahead and put the labels in the zones in which they belong to make things easier for me visually. Does that make sense how I came up with that first off? They said, take the minus 3x plus 4 and put it in x values less than 1. So left of 1, minus 3x plus 4. And then greater than or equal to 1, right of 1 is the other one, the 3x minus 2 function, huh? So basically I have to graph the left one on the left, the right one on the right, and see how they meet up in the middle. Or don't meet up. Some do, some don't. Turns out this one's going to meet up in the middle. They'll connect like Legos in the middle. The next problem we do will not connect. They'll miss each other in the middle. So they can do both ways. All right, so is this good so far? So we graph the left one on the left, the right one on the right, and see how they meet up. Now, how do you go about the graphing? Well, I'm just going to make tables. Both those graphs are just lines, aren't they? They're both just linear. They're not U-shapes, or they're both just x, y to the first power. They're both just lines. So all I need is 2 dots. Connect the 2 dots, got a line. So they're both simple graphs. They're just dots. So I'm going to come over here. Just lines. 2 dots needed. I'm going to make a little XY table for the graph on the left. Now, whenever you do this, you want to use the border. Always use the border. You need to find out what happens at the border. So I'm going to plug in x equals 1. And then some other value. Now, a good question might occur to your mind right away. Sharp students a lot of times ask me, and they say, wait. It's only less than 1. Not equal to 1, Mr. Aaron. You can't put 1 in there. Right, I know, but it does get infinitesimally close to 1. So I really need to see what it's doing at 1. In other words, you don't want to think this way. You don't want to think, okay, it doesn't go to 1. It's only less than 1. That's true. That is true. It's only less than 1. So I'll just start at 0. No, that's not a good idea. There's a whole bunch of numbers, even though, it doesn't quite make it to 1. It makes it to 0.999999, which is virtually 1. So you really do need to see what it's doing at 1. Just put an open dot there, though, because it doesn't quite touch 1, but it gets infinitesimally close. You don't want to just do 0. You'll be missing a whole bunch of information about what it does between 0 and 1. There's a whole bunch of numbers between 0 and 1. So I do 1 and I circle it. That's my own notation, just to remind myself when I go to the graph, it's going to be an open dot, because it doesn't really hit right on 1, but it does get infinitesimally close. You do a lot of this in calculus, where you have open dot spots, where things get infinitesimally close, but don't quite hit. So plug in 1 to what? To the minus 3x plus 4. So minus 3 times 1 plus 4, what is that? Minus 3 plus 4, 1. So 1, that means over 1, up 1, open dot, at over 1, up 1.
I think 2 semesters ago, you explained to us how 0.9 bar is essentially 1.
Right, so it's, So it gets infinitesimally close to 1. Open dot there. Now you need one more dot, huh? Just plug in a point, do something, get another dot, connect the 2 dots, you got the line. How about just do 2? Plug in 2, find out what that works. That's a terrible idea. But that's what I see a lot of students make. So let me help. So let me clear that up right now. Putting 2 into that table would wreck everything. So let me help you see that. If you really see that, then you'll be fine with these. That's the mistake that people make who have trouble with the piecewise. Why is putting 2 into that table not a good idea? Yeah, remember, it's all about this range here. Remember, it says you can only plug in values less than 1 to this function. He doesn't exist to the right of 1. Remember, I'm only doing the left section. You can't plug in 2. 2 is over here. That'll be for the other guy. Right? That makes sense. So always keep that in mind. Keep the zone in mind. I am left of 1. You can plug anything you want in that's less than 1. Not 2. So let's go, okay, well then, how about 0? or negative 1, or negative 2, or whatever you want. Anything less than 1 is fine. I'll plug in 0, minus 3 times 0 plus 4. What's that, 4?
Yeah.
So 0, 4, that'll be a solid dot. 2, 3, 4 right here. Solid dot over 0 up 4. So connect the two dots. There she goes. There's the graph in the left section. Everybody good so far? See how I found that?
So the line is touching the open circle?
Well, the open circle is not making it all the way to 1. Open circle means it doesn't quite touch here. Am I confusing you? So this line, all these are solid dots, solid dot, solid dot, right to there, and that's an open dot. Right at the end, it has an open dot because it doesn't quite make it all the way to 1. It gets infinitesimally close to 1, 1, but doesn't quite touch it because it's only values less than 1.
Can I find the dots that do rise over run as well?
You could. You could. Yeah. Hey, I've got a question about rise over run. What's this? This line is going up, and what's the slope?
3 over 1, or negative 3.
What's the slope?
Down 3 to the right.
Negative 3.
Yeah.
Wait a minute. The line's going up, and the slope is negative?
You can go both ways though, can't you? Technically.
You can just go both ways?
Well, like, no, not like
You
both
can
ways,
go
but I mean,
past
like,
1.
you can go down into 1, but you have to go up, because it'll still be the same thing. Like, I don't know, I just remember that from algebra, like, it was, I don't know.
Does this line go up?
Coming
And
down,
maybe it comes down.
coming down.
Yeah. So don't be, I noticed lots of people get confused. It's as you go to the right. Don't let that arrow confuse you. This is a line going down as you go to the right. If you're standing right here and you're moving to the right, you're going down.
Yeah. That just means you're going.
But it's confusing when you look at that arrow at first, huh? You go, well, it's going up.
Forever.
But that's the wrong direction. So when we talk about slopes, we always mean as you go to the right. No matter where the arrows are showing on the graph, it's as you go to the right. So as you go to the right, yeah, that line is going down, which is indeed what that slope says. It's all in perfect agreement.
But if it
It's
was
all good.
it was
It's a downward
the
line.
vertex of the minimum, then it would be.
Wait, how does it keep going down if it just never touches that 1?
What's that? I'm sorry?
So, like, you said it keeps
No.
going down.
Yeah, so it
Does
stops
is it
here.
gonna eventually curve? Oh, no.
No, it stops.
No, it's a straight line. It just stops right here. It has to, well, it gets infinitesimally close. Right there. It never quite touches,
I was just
but gets
thinking
infinitesimally
like,
close.
how, like, some of them
0.9
go
bar.
sides, but they
No.
never touch the
Yeah, no, it follows point.
All right, now let's do the right section. So in the right section, you also want to check the border. So I'm going to do one. You want to see what they both do at the border. This one's going to fill in. They're going to connect like Legos. The next problem we do, they're going to miss each other at the border. So plug in 1. So what do you get to 3? Now I'm plugging into the right function. 3 times 1 minus 2, that's 1. See how they connect up right there? 1, 1. That's solid dot. This one's solid because he's greater than or equal to 1, huh? So he hits right in the money at 1, 1. And then plug in 2.
You get 4. And then it's like always 4. Like, oh no, it's like it is. You plug in 3, you get 7.
Yeah, over 2, up 4. It's right here. And it goes that way, and we're done. Well, we got to answer their silly questions, but we got the graph.
So there would be a closed dot.
Yeah, so it turns out this dot's just normal when all is said and done because the solid dot fills in the open. Now, on the next problem, we're going to have an open dot on the line and a solid and 2 opens. And they're not going to connect up. Sometimes they do connect, sometimes they don't. It's like it ends up being like an absolute value V graph, huh? Just kind of moved over.
Mm-hmm.
Yeah,
When, if you do it the,
NAS.
like, yeah,
Yeah.
if you don't plug it in, like how you did it, the XY, would that still be an open dot? Like if you go to the 4 and then you go down 3 and over to the 1, that'd still be open dot.
I'm confused on your question. So if I plugged in,
On the left equation.
on the left one, if I plugged in different numbers,
Well, if you just did it like how she did it, if you go up to the 4.
oh, just do the slope thing.
Yeah,
So if I just start with this dot, you mean?
yeah.
And then, it doesn't matter how you do the graph. The real graph has an open dot there.
Okay.
That's what it has to do. Because the reason is because of this,
Yeah.
right? It's only less than 1. It's not equal to 1. It's only less than 1. So it can never, whatever it does at 1, it never quite reaches it.
The open dot.
That's what it's saying.
is
Less
the
than
good
1, not equal to 1, not right on. Yeah.
When I do the rise over run, it doesn't give me the point 2.4.
It's
equivalent
The
to
2.4.
It doesn't give you,
When I do the rise over run on that second.
when you do rise over run, and I heard you say it doesn't give me 2.4. 2.4 is not a point.
The point on the graph.
It includes that.
2.4.
2.4
Yeah, it doesn't give me.
is not a point on the graph. That's, the 2.4 is really confusing me. Why are you saying 2.4? 2.4 is over 2 up. Oh, though this one. I'm sorry, I'm looking at the left side. 2.4. Yeah, so if you start at 1, 1, the slope is 3 over 1, go up 3, 1, 2, 3, over 1.
But they always did this.
If you add 3,
Why would it be negative 2?
That's why it's
When you're doing the.
That's what I remember.
the slope is 3? Oh, right. That would be negative 2 on the y-axis.
That's what I'm saying.
Yeah.
That's where my point is.
Oh, yeah, y-axis. And then you would go up 3, 1, 2, 3, over 1, which is this dot.
So that's my point on that one is not that.
Right, because this stuff
Same
doesn't
thing.
exist. Even though the line would like to go there, the condition said you can't go there. Only greater than or equal to 1.
So the
Does that make
rise over
sense?
run
No, it still works. You can still start here, just don't fill this in.
Oh.
Does that make sense? Just start at negative 2 and go up 3 over 1, but don't draw any of this in because he's blocked right there by that wall. That's your first dot that actually exists. And then just go up 3 over 1 again and connect those two dots.
because we cannot come down because you say that the.
Yeah, we can't go left of 1. All right, now their questions to us are going to be about domain and range and intercepts. Let me clear some space here.
Negative.
So first off, what are the intercepts?
There's only one
There's one
intercept.
of the y-intercepts.
It's 0, 4.
Yeah, this is the only intercept right there. So the intercept is 0, 4. That's the only place it hits one of the grid lines, right? Intercepts where you hit the grids. That one, right? Rebecca.
They want us to do intercepts and brackets, is that right?
This is a point. Yeah, this is just a point. So those are always parentheses. That's over 0, up 4. Now let's do domain and range. So domain on a graph, remember that's the width. It's always left edge, comma right edge for the domain. So how far left and how far right does this graph go?
0.
Forever left and right. So the domain is negative infinity to infinity, right? The graph goes forever left, forever right.
So would they ever ask you for like, because I know we're kind of putting like two functions together to make a graph, would they ever ask us for like the intercepts of both of them?
That's what they mean. They mean the intercepts for everything on that picture.
Yeah, but the reason why we didn't have like a intercept between the two graphs because they don't touch because the other one's not at 1, right? I'm talking about like
Intercepts are places where it hits the grid lines. So the X grid line and the Y grid line. So everywhere.
I remember we did something like I think it was like a last chapter or whatever when like the two graphs touched each other. We looked that point up. Was that on our graphing calculator?
That might be something else. They're not going to say here. We're just
Okay.
doing intercepts. Just places where it hits the actual grid lines. And then what's the range on this one?
It's going to stop at 1.
Range is up and down. Huh? Maybe I'll go over here. There's where there's room to write. So the range
Bracket 1.
is bottom, comma top. There you go. So bottom, comma top. So how low does the graph go? What's the lowest point the graph reaches? Yeah, height of 1. Right? What's the highest point on the graph? Infinity. So the range then would be 1 with a bracket, to it, right? Because it hits 1 right on. This is at 1 solid dot, a depth of 1 solid dot up to infinity, 1 to infinity. Bracket on the 1.
So how about this side? Because this side is not gonna like go. If we go by this side, so we are not gonna use like a bracket.
It's all one thing now. We don't care about,
So we
it's just
don't worry about
overall
the
picture. Overall picture. Both sides, all of Frankenstein. What's the lowest Frankenstein goes? What's the highest Frankenstein goes? The lowest he goes, any graph anywhere, is a depth of 1. The highest he goes is infinity. Does that make sense?
So we don't care about the other one with an open circle for the range.
So it's just overall graph. So is their graph down at 1? Yep. Doesn't matter which one it is. Right? When it's all said and done, it's one Frankenstein. And so we're just saying bottom to top on that. Okay, so there's number 13. And same kind of thing, let's graph it. And once we've graphed it, we can answer all their little questions. Now, which will be domain, range, and intercepts. try that. Yeah.
So I'm setting up.
Yeah. So it's all about those conditions. Look at those conditional statements. Where do you want to put your borders?
1.
So definitely 1 is, again, another important border. So go over here to 1.
And anything less than 1.
So at 1, we have an important border. At 1, and here's 0. And where's the other border? Yeah, -2. Does everybody see that? See how we have a border at -2 and a border at +1? Everybody good there? So that's what we need to set up. Yeah. What about this? Let's just handle him right now. He's saying if x is 1, remember f is y is 5. That's telling us over 1 up 5, isn't it? 1, 2, 3, 4, 5. This dot right here.
So we don't.
That's all it's given.
It wouldn't be an open.
Yeah, no table for that one. That's just a single dot, isn't it? It's saying when x is exactly 1, y is exactly 5. Over 1, up 5. It's telling us the solid dot right there, isn't it? So that's all that comes of the middle information. Does that make sense? That's exactly what it's saying, right? If x is 1, y is 5. 1, 5. Over 1, up 5. So now do the left section and the right section.
And we should do 1 for all of these because that's-
One's the border. You'll want to do 1 for both of them. Yeah. So yeah, so I'm going to do the left section here. Let me start with the one on the left. When I do the one on the left, I think it would be, since the one on the left has the 2 borders, why don't we just do those 2 borders? I'm going to do 1 and I'm going to do -2. Does that make sense? So when there's edges to the thing, go ahead and check those edges. Right? Isn't that what this left function says? For x values between... Now the 1 I should circle because it's going to be an open dot at the 1. How are we doing? Am I losing you completely? Everybody see what's happening here? So in other words, the first function, the y equals 2x plus 6, you're supposed to put that in the zone between -2 and +1, but not touching the 1. So when I make my table and I put in -2 and 1, I circle the 1 because it's going to be an open dot at the 1, right? It's not going to touch the 1. So plug in. And you know, it'd probably be a good idea to do 0 as well because they're going to ask me for the intercepts in a minute anyway. And so might as well find out what it's doing at 0.
for all of them. Oh no, for
That's the only one that goes over 0. The other, right? The other one is right of 1.
That one's all right 'cause it's like only 2 away. The slope is like 2.
So just plug in y equals 2x plus 6. So 2 times 1 plus, was that 8? So over 1 up 8. 6, 7, 8. So right there, over 1 up 8, open dot, plug in -2. What's that, 2? -2, 2. Solid dot right there.
0, 6.
And 0, 6. Solid dot right there. Everybody seeing that section? How are we doing? So it's all about what x values you plug in for which functions. So right in the table then between, so everybody seeing what we're saying? So you're supposed to plug into the 2x plus 6 function for any x values between -2 and 1. So I made my table and I did x values. See how -2, 1, and 0, those are all x's between -2 and +1. 0 is between -2 and +1, isn't it? And now why did I circle the 1,8? Because it's only less than 1. It's not equal to 1. So it's got to be open dot at 1,8. It doesn't quite touch there. It only, the left graph only exists less than 1, not right at 1. Right at 1, we know this function is at a height of 5, huh? Solid dot from that middle information. Good, yeah. Nas?
And just to confirm, you didn't put a dot on the -2 because it's equal to -2.
I put a solid dot there, yeah, because it includes that. It's equal to -2, yeah. So that's solid. It hits that right on the money. It doesn't just get close to it. It hits it right on the money. Right, yeah, because it's equal. It's greater than or equal to -2. Yeah, exactly. Everybody see that? That's why that one's solid. And now we're going to graph the right section. And so when I graph the right section,
We should start at the border, right?
start at the border, so definitely do 1. Even though circle it, it's not going to really hit 1. It's only greater than 1, huh?
Right.
It's only greater than 1. So do 1, but circle it. Plug in 1 to the function minus 2x plus 5. Is that 3? 1, 3. So over 1 up 3. There's an open dot at 1, 3. And now just plug in something to the right, like 2. Doesn't matter. 1, 2, 1, over 2 up 1.
And it goes down forever.
Yeah, because that one's greater than 1, so it just goes on and on and on. Right? Everything to the right of 1 on the x-axis goes forever to the right, and thus forever down as well. How are we doing? Is that making sense? How I got that graph? Ready for the battery of questions they always give us?
Yeah.
So domain, range, intercepts. All right. So, well, questions I can answer on the graph first. Is that good? How I made that? Okay, I'm going to erase stuff so I have room. Well, let's do the intercepts first up. So the intercepts, there's 2 of them this time. There's 2 places that our Frankenstein graph hits axes.
0, 6.
Right here, yeah, 0, 6.
Is that 2.5?
Yeah.
0?
Yeah.
Well, that's the question. We got to find out what that is.
Looks like 2.5.
Yeah, it turns out it is, but we got to find out to be sure. Yeah, so we got 0, 6, and then we got this one right over here. Right, so we're hitting the y-axis right there at 0, 6. That one's nice and obvious and easy. This one over here is hitting somewhere between 2 and 3, maybe 2.5.
We should flag it.
Turns out it is 2.5, but let me show you how you would be sure, because you want to be sure, right? So how do we find out where this dot is exactly? Well, remember what we learned about how you find intercept points. We had it last week. And you guys never forget anything we talk about in here, right?
Right.
Y-intercept equal x equals 0.
Set the other letter to 0. To find a y-intercept, make x 0. To find an x-intercept, make y 0, right? Because look at this point. This is something comma 0. His y value is clearly 0. His height is 0. Right? So if I take the equation and plug in y equals 0 and find the x, that's got to be it. What equation, though? That's the crucial thing here. This is Frankenstein. Which piece of his body?
It has to be greater than 1x.
No, negative. 5 over 2. 5 over 2.
This one. This in this section, that's the function, right? In this area, y equals minus 2. I forgot to write it up here. That's the function that exists here, and over here, or right in here, I mean, it's the 2x plus 6 function, huh? Right? Those are the functions that are, I should have written that up, sorry. Those are the functions that are ruling in those areas. So in the left section, it's 2x plus 6. By the way, he stops on the left edge. He doesn't go forever, does he? Because they told me he stops at -2. He goes from -2 to 1. Doesn't go beyond. So this guy is between -2 and +1. That's his borders. Right? So, all right. So to the right here, we have this function. So if I want to find this point, I got to plug into this function. He rules over there on the right. So plug in what? Plug in y is 0. So 0 equals -2x plus 5. Subtract 5 from both sides. I get -5 is -2x. Divide by -2. X equals 5 halves, which is 2.5, it turns out. So I think they want you to leave it as a fraction. So 5 halves is the x value. So the other intercept is 5 halves comma 0, 2.5 comma 0. Does that make sense? How I found that? Right, so I took the equation that governs the right section, the one that's for values greater than 1, the -2x plus 5, and I plugged in the y value of 0 and solve for x, 5 halves. That's 5 halves 0. So I got the intercepts. Let's do domain and range now, and we'll be done. This thing's a mess. Domain and range. So what's the domain of this graph? Let me put it down here. Domain, how far left and how right? It's left edge, right edge. What's the left edge? And I don't mean this piece or that piece. I mean all of Frankenstein.
-2.
What's the furthest left any part of Frankenstein goes? -2.
It's going to be bracket.
Straight up bracket, huh? Yeah, it's right on the -2. Solid dot at -2. How far right does any part of Frankenstein go?
Forever.
Forever right. Right and down forever. Infinity, huh?
Yeah.
All right, now the range. The range. So we're going to do the range if I have any room at all here. Range, which is bottom, comma top, isn't it? What's the lowest part any part of Frankenstein goes?
Oh, no. -2. No. What is that?
Negative infinity.
-2.
Right? This purple piece goes down, 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 down. So there's part of Frankenstein that goes down forever. Right? The lowest. So that's the bottom. Remember, range is bottom, comma, top. What's the top of Frankenstein? What's the highest he ever goes? It's the highest part you see of Frankenstein anywhere. This right up here. That's the highest part of Frankenstein up there, isn't it? At a height of 8. But it's a parenthesis 8. Because it's an open dot. It doesn't quite hit that 8 right on the money. Negative infinity, comma 8 with a parenthesis on the 8. We're done. Is that good? Feel comfortable with that? They do this in calculus a fair bit. Functions and pieces. All right. I'm going to keep. So number 16. Basically, they want you to take that picture. And so they're doing it backwards now. They give you the picture, you give them the equation. So they're going to say f of x equals what if what? And what if what? So do it backwards. So no secrets with me. I think these are really valuable. So what does that mean?
You're going to put them on the test.
Next Thursday, there's for sure one of these backwards ones on the exam. Because this is how real life really works, engineering, science. They do things, it's more this way than the other way. Right? They look at something in the real world that behaves a certain way, and they have to work backwards to the equation. That's more valuable. Yeah, Rebecca?
So, if they wanted us to see that it was not equal to, they would make it more obvious.
Yeah, right. There's no open dots here.
Okay.
Everything's equal. Right. They'd make a big old whop. We'll see in the next one. They'll make a big old whopping open dot. Yeah. Everything's equals here. There's no open dots. So let's take one piece at a time. Let's take this left piece. Oops. This left piece. And let's write an equation for him. First off, where does he exist? In what x zone does that left piece exist? From -1 to 0 on the x-axis, right? So that's if x is between -1 and 0. That left piece is x values between -1 and 0, isn't it? On the x-axis between -1 and 0, that guy exists. So in that, if x is between -1 and 0, if that's true, that equation. So what's the equation for that thing? Well, it's a little piece of a line, isn't it? So it's going to be mx plus b. The other one is too. So mx plus b, right? A little piece of a line. What do you remember about line equations from your algebra days? Is it me or do I refer to your algebra days every day in class here?
So it's gonna be negative x.
Okay, so what's the b? Let's start with b. Do you know in the mx plus b, do you remember what the b is? It's the y-intercept. It's where the graph strikes the y-axis. So where does this piece of line smack into the y-axis? Right there at a height of 0. So that part's 0. Okay. Now, what's the m?
It's a slope.
Slope. That's rise
-1, 1.
over run, right? That's what slope is. Rise over run. So you go from one dot on the line to another dot on the line. Doesn't matter which dots. Any two dots on the line will be fine. Well, I've only got 2 in this case. So between those 2 dots on that line piece, what's the rise and run? Go down 1, go over 1. So it's down 1, over 1. So it's -1 over 1, x plus 0, which is, more simply stated, get all this out of there, minus x plus 0. So I'm not going to write that. You with me? Right? Everybody see this
Okay.
is that part. It comes out to be minus x plus 0, just minus x, right? Because it goes, everybody see the rise and run from edge to edge, down 1, over 1. So rise over run, -1 over 1, negative x plus 0, because it hits the y-axis at 0. So there's that piece. Can you do the bottom one? Or the right one, I mean? Can you do that right piece now? Write in the x conditions and find the equation. Give you a second. Or maybe 10 seconds. So first off, where does this graph exist on the x-axis? From this dot to this dot, from here to here, from 0 to 3, huh?
Mm-hmm.
We good?
And we have a closed dot, so it's also an equal to.
Yeah, we do equals on both. 0 and 3. Bless you. 0 and 3. Good there, first off. That's the where it exists. And now the equation's another mx plus b. It's another straight line. Just got to find the b and find the m, the rise over run. So what's the b? Where does this piece of line strike the y-axis?
Again.
Right here at a height of 0 again. So that part's just 0 again. And what's the slope? Slope is always rise or run. So take any 2 dots, say like this dot, this dot. What's the rise? 1, 2, up 2. 1, 2, 3, over 3. Up 2, over 3. 2/3. So the slope is 2/3 x. You don't even need to show the plus 0. 2/3 x. Done. How are we doing? Does that make sense? I just took from dot to dot, go up 2 over 3. Rise over run. 2/3. X, that's the slope x. And the b is 0 because it hits the y-axis at 0. At a height of 0. Questions? Samuel?
It says it doesn't go on for forever, right?
Right, yeah. See how this one is a dot on the end? It ends here. Whoops, I erased it. It ends here, and it ends here. Yep, doesn't go forever. And that's what I'm saying. It ends.
So the range is.
That makes sense? That's what I'm saying right here, right? This goes between -1 and 0. And notice it's not just x greater than 0 or something. That'd be forever. Anything bigger than 0. 10 million. Right? That's not what I said. I said it's between -1 and 0. -1, 0, boom. Stops on those 2 edges. And this part, between 0 and 3. Boom. 0 and 3. Not beyond 3. Not less than 0.
So you're going to have brackets?
Oh, I'm done.
Oh, you're not, you don't have.
They don't ask me any other
Oh,
questions.
thank God.
That's all they
If
want.
you were though, it would be brackets.
Now ask a question.
Yeah. Is there a reason why on the left side you
And then the range would
went
be 0.
down
Because
one
zero
from the
It would
second
be
point,
0.
down 1 and over to the right? and then on the right one, you went
For
up
this function.
and
They only want to just
over to the right, to the rise over run.
erase it.
Find the-
As opposed to what? Like, what else would I do?
It's giving you
Well,
a set.
if you just start at the zero,
Okay, so there's
I
no.
mean, it would be the same thing, right?
It would. Yeah, it doesn't matter where you start. Yes, if you start, you mean if you start here and go back and up like that?
Well, you rise one, then go over left.
Okay, that's fine. Yeah. So you'd go up one and back one, up one, back one, rise over run, still be the same. Yeah, it doesn't matter how you move.
But on the right one, if you would do it the other way and go down and over to the left, that would be wrong, though, right?
No, it'd be okay. Here we go. So you go down 2, back 3. So back 2 negatives, positive 2/3. It's all good. Yeah, it doesn't matter how you move between the 2 points. When you do slow, it doesn't matter which one you start with. Just remember, down is negative, left is negative, up is positive, right is positive. It's all good. It's the same slope, however you do it. Is that good? Math always works. Isn't that beautiful? As long as we are logical and follow what's true, it'll give us true answers. Section. We got to get on to that next section. All right, so this is number 17. Same kind of thing. They want you to work it backwards. So they're saying there's something, if something, and there's something, if something. Left piece, right piece. So try that. Those are terribly written ifs. If. All right, so start with the left piece. You need an equation for this guy. So mx plus b. Find out the x zone in which he exists. So what's the x zone in which he exists? He goes from 0
To negative.
to back forever.
Yeah.
See that arrow? That one has an arrow this time, huh? Not a dot. So that one goes left. This part is saying I'm going left forever. So how do you say from 0 and left forever?
0.
Less than or equal to 0. Right? We don't put two numbers with a negative infinity. We could have. That's how you write intervals. But for whatever reason, with x greater than less than, well, I know the reason, because it's simple. All you got to say is less than 0. You don't need to mention infinity. If you're less than 0, that means you're off to negative infinity, huh? Make sense? Any numbers less than or equal to 0. We do want the equals because this is a solid bar here, huh? Solid dot there, I mean. Right? That good? All x values 0, less than 0. All values left of 0. Now, write the equation for that piece. mx plus b. Go between any two dots. Do the slope. And where does he smack into the y-axis? 0 again. Right? So here we go again. Same kind of thing. mx plus b. The b is 0. Because he hits right here. He smacks into the y-axis at a height of 0. The other piece doesn't. But we'll get to him in a minute. So 0. And so now figure out his slope. Rise over run. Go between any two dots. Like I could go from this dot to this dot. Go down 1, 2, 3, over 1, 2, 3. So down 3, over 3.
So it's going to be negative 1.
So it's negative 1. So it's negative 3 over 3x plus 0. It's negative x.
Wait, so you wouldn't go up on that one?
You could.
Well, you could, but you have to go left.
Let me show you. So
Oh, that's right.
if you started from here, you'd go up 3, but then back 3. So it'd be up 3 over back 3. It's still going to be negative 1. See how it doesn't matter which way you go?
Math has to be true forwards and backwards.
It is, isn't it? Beautifully true. As long as we're true, it's true. Minus x. So that piece is just minus x. Now can you do the piece on the right?
Yeah.
Let me do that with you now. So we getting that? So this right piece, so where does he run into the y-axis? Right here. At a height of what? 5. Now you think, yeah, but he doesn't hit there. Whatever, he's aiming towards it. That's all we're doing with this line equation is where is he aiming? Yeah, he hits at 5.
That's your B.
It's not our issue that he was stopped by the conditions, whatever. He's headed to 5. And so now we just need the mx. What's his slope? Getting the hang of the slope stuff? So you can go either way. Go down 1, 2, 3, 4, 5, down 5, and over 1, 2, 3, 4, 5, down 5 over 5. So down 5 over 5x plus 5. That's negative x plus 5, isn't it? Is that good? Now, you might have gone, maybe you were thinking, well, I went to the 3, too. That's fine. Whatever. I'll do that one if you prefer. Go down 2, 3, down 3, over 1, 2, 3, over 3, down 3 over 3. Same thing.
Since it doesn't touch 0, would it be if x is greater than 0?
Oh, yeah, and we got to get the condition. X is greater. Oh, no, it's between 0 and 5, isn't it?
0.
Yeah. So it goes, I forgot to get it goes from 0 to 5, but it doesn't touch the 0. It does hit the 5. Yeah, I forgot about the conditions. Is that it? Is that good? Minus this is, so the answer comes out to be minus x plus 5. There it is. Is that good? So this graph exists between 0 and 5 on the x-axis, but he hits the 5 with a solid dot equal to 5. He doesn't hit x equals 0, open dot, no equals to 0. And the equation is down 3 over 3, so negative 1x plus 5 because he hits the y-axis at 5, or he aims towards the x-axis, y-axis at 5. Good? All right. Wind chill. This is interesting. You know how wind chill works, right? It's a certain air temperature, but when the wind blows, it feels colder than that. So here's a formula for that. I think it's kind of an interesting little formula. I don't know if this is exactly the one that they use, but it looks kind of official-like. So, so basically, I'm just going to brush over this quick. You probably won't be 100% comfortable, but I got to move. T is the air temperature. Let me just give you the basics. T is the air temperature. V is the wind speed. It stands for velocity, wind speed. Okay. And W is the wind chill factor, meaning how it feels, temperature that you feel. So what are they saying? Well, it's in pieces, isn't it? They're saying if V, the velocity of the wind, is what? Fairly low, between 0 and 1.77 meters per second, the wind chill is just the same as the air temperature. It doesn't feel any different at all. W is just T. T is the temperature, what the air temperature really is. They're saying the wind chill factor won't feel any different. It'll feel the same when there's not much wind. But if there's a medium amount of wind, between 1.77 meters per second and 20, I don't know what that is in miles per hour, then the wind chill factor is this big complex formula. And if the wind is really blowing fast, more than 20 meters per second, the wind chill factor is going to be that formula. All right, let's crank out what they've done here. So it's a real-life example, I always like real life, of using a piecewise function in science. So, suppose it's 10 degrees air temperature. Your thermometer on the wall says 10 degrees Celsius.
And you don't live in California.
Then what does it feel like? What's the wind chill? If the wind is only blowing at 0.75 meters per second, not very fast. The wind's barely moving. Not even 1 meter a second, right? So which one am I going to plug into? The top, the middle, or the bottom? Yeah, it says if your velocity is between 0 and 1.7, between $0 and $1.77, 75 cents is between, is in there, then it's just T. It's whatever your T is. T, temperature, is 10. That's why the answer is just 10. In other words, if there's hardly any wind, the air temperature is exactly how it feels. It doesn't change it at all. That makes sense, right? Low wind speed, you just use the top one. W is just T. They're the same. There is no difference between the wind chill. It's not chilling you. And the temperature, it's hardly blowing. Right? All right, next part 2. They're saying, okay, what if the wind was same, notice all three of these have the same air temperature. The thermometer is saying 10 degrees in all three cases, A, B, and C. Right, that's the temperature, that's the T, it's the T, the T, the T. In all three is 10. Now, part B, they move the wind speed up to 9. If the wind speed's blowing 9, which formula are you going to plug into, top, middle, or bottom? If the wind speed is the V, the velocity. This is velocity, isn't it? This over here is V. This is your V. It's velocity, wind speed, velocity. If it's 9, I'm plugging into what? Top, middle, or bottom?
Middle.
Yeah, because 9 is between 1.77 and 20. So you're plugging into that messy formula. Plugging in what? The T is 10. You plug in 10 for T here. The V is 9. Plug in a 9 there, plug in a 9 there. Hit the buttons on your calculator. You'll get that it feels like 1 degree. Even though it's really 10 degrees, air temp, it feels like 1 degree because of the wind. Finally, third one. What if the same air temp, thermometer is still saying 10 degrees, and now the V, the velocity of the wind, is blowing at 37. It's howling. It's howling outside. So your velocity is 37. So I'm in the third section, huh? 37 is greater than 20. Then you plug into that form. Plug in the T, the temperature right there is 10. Hit the buttons on your calculator. It feels like -3, even though it's still 10.
Minnesota.
Or someplace super windy. All right, there we go. I'm not sure if you caught